All right, so our whole unit 3 here is all about bonding, okay? So we have to remember that we've talked about our elements now. Now we are going to talk about compounds. So if we remember, compounds have 2 or more elements in them. And they are chemically combined. Chemically combined. Okay? So an example, of course, would be NaCl, where we have sodium and chlorine that are in this compound. Okay? So a bond is really the sharing of electrons. Okay? So only our valence electrons are going to participate in bonding, because these valence electrons are the electrons that are on the outer edges of our atoms, okay? So bonds are formed as a result of a shared attraction and I would say even a shared electrical attraction. Okay? If we know about electricity and Coulombic forces, we can really understand a lot about our bonds, right? So our law of conservation of energy, mass, charge, essentially during a reaction, right, a chemical reaction, energy, mass, and charge cannot be created nor destroyed. That means that all three are conserved, okay? So in our chemical reactions, right, we're going to be forming and breaking bonds. So oftentimes, right, what we can do is we can use our periodic trends to understand the ions that are going to form and how those atoms or how those elements are going to interact with each other, okay? So if we remember, right, we should have filled in our periodic trends page, right? I'm going to write down at the bottom of the periodic trends page, but our periodic trends, we said that some atoms, right, they're going to have a really low ionization energy. If it's got a low ionization energy, it's going to lose electrons really easily, right? If it's got a really high electron affinity, right, this is its desire to gain electrons, it's going to gain electrons really easily, okay? So these two things are really going to be playing in tandem, okay? So if we look at our elements, right, our elements over on the left-hand side, I'm actually going to bring this back, our elements over on the left-hand side are going to have really low ionization energy, right? Over on the left-hand side of our periodic table, it's going to have a low ionization energy. It's going to give up those electrons really easily, right? Those would be giving up maybe the electrons in the 3s orbital, so that then it has a full 2p and 2s orbitals, right? It's going to get rid of these higher energy level electrons so that it's stuck with just the lower energy level electrons, okay? So over on the first column, right, the first column of our periodic table, they're going to become +1. Right? It's going to lose that one electron that's in the s orbital, that's in a higher energy level, and just be left with the lower energy level electrons. In the second column, right, I'm going to make something like this so it kind of looks like our periodic table, right? Our second column, it's going to be +2, because it's going to have 2 electrons that are over here in the s orbital in a higher energy level, right? So it's going to get rid of those 2 electrons in the higher energy level and be left with just the lower energy level electrons. Then we come on over to here, right? And I'm going to break it a little bit. We're going to do +3 because, again, it's going to go backwards, okay? Then in column 14, it's going to be plus or -4. And then we'll go +5. That seems really weird. We said if it's got high electron affinity, it's going to gain electrons. This is where we get that plus-minus thing, right? It could lose 4 or it could gain 4. Now it's going to go to -3, -2, and a -1, and then we've got our noble gases over here, right? The noble gases have our full valence shell, so it doesn't really want to gain or lose any electrons. But fluorine, right, this would be our fluorine right there, fluorine really wants to gain 1 electron, right? So it's got a really high electron affinity, really high electronegativity. It really wants to gain that 1 electron so that it can have that full valence shell, okay? So just by looking at our periodic table, we're going to know what our ions are that we form, okay? So our octet rule is essentially that 8 is great, right? Elements are stabilized by having a full valence shell. Okay? So by having a full valence shell, they're going to be stabilized. Okay? So here are our noble gases, right? They already have 8 electrons, 8 valence electrons. It's going to be stable. Okay? So this is why they don't really react with other elements. So which noble gas would be most likely to form a bond with another element? Looking at this periodic table here, right? We say, well, helium doesn't really have a charge, neon doesn't have a charge, argon doesn't have a charge. Each of these are pretty small. They're really holding on to their 8 electrons really easily, okay? But krypton has no charge, but it could also form a +2 charge. We've seen some elements or some compounds that form a +2 charge on krypton. Xenon does even more, right? It's got a whole bunch of different charges. So I look at this and I say that xenon could form a bond because it's really big and fat. So it's holding on to its electrons as much as it can, but these electrons that are in the 1, 2, 3, 4, 5th energy level, those electrons are really far out there, right? The further out those electrons are, the harder it is to hold on to them. So those electrons aren't going to be held as strongly, so xenon is going to be forced to share. What do we think causes noble gases to be more reactive? We just said it was going to be size. Okay? Which element, Na, O, F, P, or S, would be most likely to form a bond with this noble gas? Which one wants electrons the most? That would be fluorine. Fluorine is the big pig, Miss Mooney likes to say, right? The big pig is fluorine. It likes to steal electrons anytime it can because it always wants to have that full valence shell. Okay? So, what we're going to move on to is our ionic compounds, okay? So, our ionic compounds, there we go, right? Ionic compounds, they have one element that is going to steal an electron and one element that gives up that electron, okay? So we have a few different types, but our easiest type is when a metal loses an electron to a nonmetal. So if we think about our metal here, right, sodium, it's got a really low ionization energy. It doesn't really care too much about holding on to that electron because that electron is all the way up into the 3rd energy level, and it's got a lot of electrons down in the 2nd energy level. So it's going to lose that 3rd energy level electron, the 3s1 electron, and it's going to lose it to chlorine. Chlorine, right, has a really high electronegativity. It has a really high electron affinity, so it wants to gain that electron, okay? It's going to gain that electron and put it into the 3p orbital, right? So if we look here, right, this was the 3s1 electron, okay? And our valence electrons for chlorine would be 3s2, 3p5. So it's got 7 electrons in there, and it is like, give me one more electron, I want to be an octet. So it's going to steal that electron from sodium and become Na plus in brackets, and then Cl with 1, 2, 3, 4, 5, 6, 7, 8 electrons around it, and it's got a negative charge. So now, right, sodium has a full valence shell in the second energy level, and chlorine has a full valence shell in the third energy level. This is our ionic bonds, all right? So we have one piece that's losing an electron, and then one that is stealing it and gaining that electron, okay? All right.